Hi, everyone. Welcome to the session today. It's on prototype to production, crafting applications with Azure Cosmos DB. I'm Saranya, a principal PM on the Azure Cosmos DB team. And with me here today.
Hi, I'm Sandeep here.
And we're very excited to present this very demo-heavy session and description of best practices gotchas on building from prototype to production on Azure Cosmos DB. Just so that you all know, Cosmos DB database powers over 95% of all Microsoft internal services, Azure services, Dynamics 365, Xbox, and more. So hopefully this session will be educating if you're looking forward to taking your applications built on Azure Cosmos DB to production. Talking of applications, applications form the centerpiece of any digital transformation, and more specifically in today's modern apps have salient features and needs. Needs like, say, simple, clear UI, intuitive UX, being available and responsible pretty much all the time, providing real-time, near real-time access and updates, etc. But also focused on security, privacy, monitoring, cloud integration, and like table stakes, like basic hygiene factors. Not to mention pretty much almost all applications that we see today, new applications, want to have AI enabled, specifically Gen AI capabilities and immersive experiences to be synchronized and always available, accessible data. Talking of data, I do want to highlight that data forms the very fabric of modern apps. It's quite evident that it provides the basis for users' experience, engagement, satisfaction. So we are here today to present to you Azure Cosmos DB, a database which is available anytime, anywhere, always on. Specifically, would like to call this a SQL and a NoSQL data store, a database that was envisioned with some core tenets and differentiating factors. Factors such as auto-scale, serverless, ability to scale pretty much planet scale, optimized TCO, tenant isolations. These all provide basic tenets for elasticity and scale for multi-tenanted apps. On the other side, Cosmos DB's consumers are application developers. We are looking forward to provide flexible development SDKs, emulator support for development outside of the cloud, provides SDKs in Java, .NET, JavaScript, Python, and now Go as well, and other enhanced features such as GraphQL support, etc. The third tenet I wanted to highlight is Cosmos DB provides multiple data structures. It's a multi-model API, although you choose a particular model and stick to it, but we do have what we call the core NoSQL API. That's the baseline infrastructure stakes for us. And today's session is primarily focused on the core API. Outside of that, we do have Mongo, Cassandra, Gremlin, and Postgres APIs as other data structure models as well. The core differentiating tenet of Cosmos DB, it's his high availability and scale, reliability as well. So Cosmos DB promises a single millisecond read and write latencies, globally distributed database, potential provides RTO of 0. We provides finite financially backed SLAs and multiple consistency models from strong to eventual when you're looking at a globally distributed data store, truly making Cosmos DB quite differentiated and efficient. Not to say that Cosmos DB also has an analytical store co-located. We also have Fabric mirroring to provide real-time analytics. With this context, I do want to just kind of highlight that over today's session, the applications that we will see will be AI apps and so on and so forth. So Cosmos DB supports AI apps very natively, specifically because of the core tenets we spoke about: real-time access, performance, scalability, ability to read and write data at that speed, global distribution, pretty much flexible schema. NoSQL data store provides various kinds of input data, could be text, could be video, could be media. So provides ability for us to have fluid schema, etc. and supports AI capabilities such as vector search, vector index built in natively, ability for you to run copilots on queries, natural language queries that we can optimize and create the actual queries for you, RAG pattern based for building data copilots for your application. And last but not the least, on integrations, Cosmos DB is integrated with the Azure, say, AI Studio plugin. It provides as a metadata store for all chat and enterprise search applications. If anyone's building any application using Azure AI Store and other accelerators that we have. In case you did not know, OpenAI's ChatGPT, Cosmos DB, we run petabytes of data, trillions of transactions with single millisecond read and write latency. Let's start today's session with a little bit of internals on Azure Cosmos DB. The key concept and pretty much the singular concept that I will leave here, and then we actually go on to our demo sections, is the construct of request units or RUs. It provides us a currency for abstracting IOPS, memory, and CPU, and has some sort of a conversion like one request units roughly is about 1 KB of data being read. So literally the cost of Cosmos DB, any applications running on Cosmos DB, consists of one component, which is the request units or the pricing component associated with the queries you do or the reads and writes you do, the throughput model. And on that pricing model, we do have some variations. You can choose to have X number of RUs and call this a provision throughput, or you could have an auto scale model to say we will automatically scale, and we do recommend auto scaling. The other option, serverless model, is purely just based on the calls you make and aggregates the request units charged. The other component of pricing is the storage price, pretty much very minuscule compared to the query cost, etc. But that's for your data being stored. With this context on Cosmos DB and internal, I'll probably hand over Sandeep to you to give us through a real world use case background. And let's start looking at how do we take an AI enabled application to production and some cool best practices.
Sure. Let me first introduce you to the background of a use case that we are going to use for our session today. So we are going to use a chat application that Contosa system has built. They originally had an RDBMS-based app, and it used to be a single app for each customer. And now what they're trying to do is to consolidate all their apps into a cloud-native app. And since these are AI times, they want to have Gen AI capability. They want to use RAG pattern to provide responses to the customer's chats. To do that, what they've done is they've taken our hackathon content and then gone and made some changes to it to add multi-tenant, multi-user capabilities to it. What they came back is to say that the application works fine in dev test scenario, but they were seeing some performance issues in their application during load testing, and they wanted our help to see what could be what could be wrong. And this session, we are going to walk you through the issues that we saw and how we fixed them. So to start with, maybe I should walk you through what the architecture of the application looks like, and then the user experience of it. So let's start with the architecture. As you see here, the users interact with the web app, which is made in Blazor. The messages, the Blazor app interacts with Cosmos DB. And then we have Azure AI Search and Azure OpenAI to provide the LLM capabilities. So Cosmos DB basically is storing all the messages, all the chats, etc. And OpenAI Search, Azure OpenAI and Azure AI Search or Cognitive Search are used for providing responses to the user through the LLM. Let's look at the UI. Here on the UI, you see that the page is divided into two panes, the left pane and the right pane. The left pane has got the list of chats. We call them the sessions. And when a user clicks on a session, all the messages for that session load up here. And apart from these two, there is a search on the top of the left panel, which can be used to search for messages which were published in the last 30 days. And then on the right pane bottom, there's a text box where the user can put a query and click on this button. and get a response from the LLM. So basic, the UI is the very basic, and basically we're looking at four pieces of information, which is sessions, messages, search, and response. So now that we know of the architecture and design, let's also look at some helper tools. So basically, as part of the investigation process, I developed some helper tools which will help us analyze what's going on and look at the metrics simpler. So what the idea here is I want to see for each request, what is the latency, how much RUs were consumed, and what was the status code, and from which region the request was responded to. Since I wanted this metrics to be shown live and for each request, I had to write a small piece of code, and I'll show you that. But just to be clear, this is an optional component, and this was built primarily to show you the numbers live. We do have metrics on the Cosmos DB portal, and we do have log diagnostics, which can do the same. We also have a lot of telemetry coming from the SDK. So adding this tool is not mandatory. So in case you are interested in building something like this or analyzing the response per request, what you could do is you could create a class, a simple class. Basically, we are creating a class. We are starting a stopwatch to count the time. Then we are using the response, and from the storing the response charge as total request charge. And then either in case of a success or in case of exception, we are storing all this information and converting it into a metric information, in which case we collect the time and the RUs that were consumed. Finally, when somebody wants to save it, we save this metric into a Cosmos DB container, separate document for future use. And in my case, I'm using it to paint it in the dashboard I show you. So, and if you were to plug in this class in your Cosmos DB API calls, then this is how you would do it. You would initialize the class. Wherever you get a response, you will use the update method. Then at the end of the function, you will do a success, or in case of an exception, you will store an exception. So basically, after creating the class and adding these 4 lines of code in a Cosmos DB API call, you could store all these metrics and use it for analyzing it. Apart from that, another thing that we will be using in the future is the diagnostic string. The SDK provides you a diagnostic string for each response that we give, and this is how you can collect it from C#. But again, other programming languages have similar equivalents, so you could use that to understand how the SDK performed, what did it do, what are the API calls that happened, etc. So with these tools, I will be able to analyze what's going on, and we will also look at, of course, the Cosmos DB portal metrics, and using these analytic tools, we will be able to explain what's going on and come up with some solutions. So with that, maybe I can now start taking up the issues one by one, and we will move to the first issue, which was high latency and RE changes on scale up.
So let's talk of the first issue that we will focus in this video, and subsequent videos will cover a couple of others as well. But the first one was on performance, right? So essentially what the customer has been doing on this chat app, for example, is application was performing better when the container had about 10K RU. After increasing the request units to about 100K, it's supposed to become better because you're giving it more request units to work through, but actually the performance has degraded, specifically on page load and on search patterns. So Sandeep, maybe for us to just see the app and then look at the page load and search, and then we can see what we should be looking at to analyze.
Yeah, sure. So maybe let me bring up the app and see, let's try to replicate it here. So here is the app, and at this point, we are running the app with 10K RU container, the way customer was developing it initially. And whenever I do some action here, you'll see the numbers showing up on the dashboard on the left. So let's try with the first activity, which was to say, let's click on a chat session and see how much time it takes to load. So when I click on this chat session, we expect the numbers to show up here. Should take a minute. Yeah, here see. So we see that approximately it takes 6 RUs, and the latency is about 60 milliseconds, which is okay, which is nice. And this is end-to-end latency, and I'm running it from my dev box. So numbers could be a little high here because it's running in debug mode right now. So now this is step number 1. Step number 2, the customer reported, is click on the refresh button, which is the page load. So when I click on refresh, it's going to reload all the sessions again. So let's just click on refresh and see what kind of numbers we'll see. Okay, so it's about 70 RUs. And now next is search. So we'll click on we'll do a quick search and see what happens. Okay, about 120 RUs, and so this is the initial benchmark that the customer was looking at, and they were pretty okay with it. Now, what happened is the customer went ahead and changed the increased the RUs on this container to 100K, and maybe I can try to replicate that and see what happens. So I have a 100K container, and let me just try to change that and see what happens.
So the customer, once they move to 100K, they are complaining issues specifically on the page load and on the search. So it'll be good to first see these issues and then analyze to see how we can find solutions for the same.
Yeah, so I changed the collection to a 100K container, and now let's revisit it once again and see what happened. Okay, so now we are in the 100K container, and let's see what kind of numbers we see in the 100K container. So I'm going to click on the chat session, and we expect the numbers to be similar. That's what the customer said. So let's see what happened. Something similar, around 4 to 5, 6 RUs. Latency is also the similar lines. Let's click on refresh next and see what kind of numbers we see. Okay, 100 RUs, but the latency is much higher. Okay, and now let's finally do the search and see what we do, what numbers we see. Okay, we see that the RUs have also gone sky high, 900, and latency is very high. So I guess this is what the customer is complaining, that just because they went from 10K to 100K, they are seeing the latency is going up, they are seeing the RUs skyrocketing. So this is what is concerning the customer.
Yeah, the numbers look staggeringly different and very high. So if we go back to the slides for a bit and look at how do we analyze these steps, right? There are certain things whenever we do these kinds of troubleshooting, we want to keep a tab on. Definitely check the metrics for any server-side errors. We do collect a lot of diagnostic logs and metrics, so it's quite evident from our side for us to do that. So SDK diagnostic strings to understand query stats. Look for either whether there are cross-partition queries or specific queries that's actually guzzling up the RUs that's working. Indexing is another important parameter. If your documents are very heavy documents which have multiple properties, everything is indexed by default in Cosmos DB. So you want to probably exclude wherever you think the queries are not going to touch those properties, etc. So a couple of these areas. But Sandeep, I'm sure you've been looking at this. So let's look at how in this particular scenario, what are the issues?
Yeah, I think this is a very good, the steps that we provide here. I just followed the same steps. So I look at the metrics side for any server-side errors. I didn't find any. We saw the RU latency and status code and region information through the helper tool that we have developed. The same thing is available to SDK diagnostic string also. So again, we already are aware of that. maybe I should then look at the queries and try to see if there are some cross-partition queries. So let me switch to the portal and bring up the Data Explorer here. So this is the uh, Data Explorer for the use case that we are looking at, and this is a sample document here. So if you look at the sample document, it's a very simple document. There have got some 5 to 6 fields. Okay, now that we have looked at the document, let's run some queries and see how the queries perform here. So I will open the query explorer editor. This is the query that the customer is running, and let's see what response we get. So we of course get the response, but what I'm interested in is the query stats. What I'm interested to see is what is the RU count. So if you see here, this query took about 17 RUs. And if I click on the per partition query metric CSV here and open it, I should I see that there is a single line response which has come, which basically means the query got executed on a single partition, and that's what the output of this file means. So now let me then maybe execute the same query on the 100K partition, 100K collection, and see how it responds there. So chat PK is the 100K equivalent of this. I just had scaled it up and created it for a time for the demo. And let me run this query there. Okay, I get the similar response. Let's go to query stats and see the numbers. Yeah, so this is expected. The request charge has gone up. It's gone to 52 RUs, almost 3 times. And let's look at the per partition query metric CSV and see what does that show. Okay, so now this time I see 10 rows here, which basically means that the query got executed on 10 partitions. So clearly the query that is getting executed is a cross partition query. And that is one of the reasons why the customer is seeing issue. Another thing that I may want to check here is to see if there is some kind of skewness in the partitions. Since we're talking about 10 partitions, just want to make sure that all partitions are having similar throughput and similar storage. So I come to the metrics, I do, I select this metric called physical partition throughput, and I have split it by, I filtered it by the collection that I'm interested in, and I split by the physical partition ID. I see that there are 10 partitions here, and all of them are running 10K. So there's no skewness here. All the partitions are having 10K RUs. Same thing in case of data also, I see that all partitions are having about 2.8 GB. So there's no skewness in terms of throughput or storage. So the only reason why this query is not performing well is because of the cross partition query. And my suggestion would be to change it to hierarchical partition key, and then we should see some performance improvements.
Thanks, Sandeep. I think this is great. It's great that we are finding this. Maybe as a recap of where we are to look at this, where we started, for example, was to start with the issues, wherein, as you see on the screen, the verdicts, when we look at performance, we see huge increase in the search. The search has gone literally whatever, close to 500% increase in latency. RUs have become 200%. So those are the issues. And as Sandeep, you kind of highlighted specifically, partitioning is probably the most imperative and the key issue that one needs to think and work through when we are creating, designing applications. So partitioning your data and data modeling, the end user typically chooses a partition key, which is a logical partition key. The physical placements of the logical partitions are automatically handled by the platform as a service, in this case, Cosmos DB. And if you look at how this is handled is on the bottom of the screen, the partition 1, 2, and these are all physical partitions. And on these physical partitions, you have multiple logical partition key ranges. For example, if I do an insert of this key ABC123, it goes to physical partition 1, but its own logical partition, which is ABC1 to 3, it's placed. Or if I do another insert, in this case, say XYZ999, and I do an insert on that, it would go to its specific partition, which relates to this partition number 2. So that's one thing. Documents with the same logical partition key will end up in the same physical partition and the logical partition. The second thing is Cosmos DB evenly distributes the allocated request units across all physical partitions. In this case, 100K RQ is allocated evenly. Moving on to concepts on logical partition key, as you guys saw right now, it can either be a single property or a synthetic partition key, which could be concatenated of multiple properties or a random suffix or a pre-calculated suffix, etc., or hierarchical partition key. And Sandeep, maybe you can spend time to explain to us why you think in this case, hierarchical partition key was a valid fit, and logical partition keys can store up to 20 GB. Going back to the physical partition, it's about 50 GB today, as we see, it depends, and that's abstracted from the end user. Automatically, the physical partition splits and they are non-blocking splits, so it happens automatically. I would leave you guys with one last caveat on the best practices in partitioning. For write-heavy workloads, it's good to have high cardinality of your partition key. It's a logical partition key. High cardinality will ensure that there are no storage queues because they will be stored equally across all physical shards. However, if it's a read-heavy workload, so on looking at, say, point reads, which is key value lookup, then the main queries, it's good to have the partition key included in the filter. So that's a good one. This will avoid throughput skews because then, it knows the key and it just goes and acts only on that physical partition or that limited partition. So it doesn't need to do a cross partition fan out. Realistically, in this world, you have read-write workloads. We'll have to look at data access patterns, choose appropriately the right kind of partition key based on your query parameter. In other cases, you could use materialized views to change a partition key for a different view for another workload heavy. Duplicate writes, essentially to see how you can minimize cross-partition queries in your maximum query of your workload, like 80-20% split, etc. Last but not the least, we do, you can change the partition key if required as well. So Sandeep, maybe specifically you mentioned hierarchical partition key. Do you want to just show us, walk us through the solution here?
Yeah, so maybe I can go back to the portal and bring up our document explorer and talk about what hierarchical partition key is and how it works. So let me go to the document explorer here. And this is our collection that we had that we were using. Now, if I would, so one thing that to note here is if you look at the document explorer, we have an ID and a singular partition key. In this case, it's called PK. Now, if I were to use a hierarchical partition key, it's very easy to do. First of all, let me just show you how to do that. I can go to scale and settings, and I can go to partition keys, and I can click on change, and then I can give a new name to a container. I put ABC for now. And I can add up to 3 partition keys. And maybe here I will say tenant ID, user ID, and PK. That's what I had used in the past. And if I click on OK, the system will automatically copy this data to this new container called ABC and with the hierarchy partition key. It will, of course, take some time to move the data. And one thing to take care of is this is an offline data copy. So if you're making new changes to the source during this activity, it will not get copied to the target. So please do not make changes to the source when the change partition key is in action. In our case, I have already done that. And my collection with hierarchical partition key is called HPK. And now if I come here and see, you can see the headers have changed. There is, of course, the ID, and then there are 3 more columns. One is the tenant ID, the user ID, and the partition key. So basically now it has got 3 levels of partition key. Now, the interesting thing is, why did I suggest hierarchical partition key in the sense? So let's go back to our query and see what was the query. This is what we were using as our query. And if you see here, the query has got a tenant ID and a user ID. And if I execute this query, since I have given 2 out of the 3 partition keys, this query is not going to execute on all 10 partitions. It's going to get executed on a limited number of partitions. And thereby, we are expecting that the cost of the query is going to come down. And to prove it, let's just execute it and see what happens. So if, of course, the results come, and let's look at the query stat, which is the important thing. And as expected, the RU charge has come down. We were looking at 52 RUs, then it was a single partition key across 100K. Right now, it is a hierarchical partition key and 100K. So the only difference is the partition key. And why is that RU come down? Because if I click on the per partition query metrics and open this file, I see that the response has come from a single partition, which is partition 9, but which partition doesn't matter. The number of partitions that participated in this query is what matters. What we are trying to do is to make sure that query is reaching the minimum number of partitions that are required for executing this query. So this is a very easy yet very powerful way to do it. One more thing that we want to do when we do a hierarchical partition key is change the way we provide partition key to in our code. So maybe I should talk about that, and let me just go to one of the code pieces and maybe walk you through how we do that. So here in my code, I have created a function called get partition key. Again, just way to make it easy for me to show how to partition key. So in this code, if you see, we can zoom in a little bit. Okay, so here what I'm saying is this function returns me either a hierarchical partition key or a regular partition key, depending on what I pass here. Now, what I want you to watch is that in cases, I do not have the PK field with me, the partition key field with me. So in that case, in the absence of a hierarchical partition key, the only thing that I can do is return a null partition key. And when I say null partition key, that basically means the query is going to get executed on all the partitions. But when I use a hierarchical partition key, I can limit the query to by using the tenant ID and the user ID. I still don't have the partition key, which is the PK field, but by just providing these 2 partitions, I am now able to restrict the query to go to a limited number of partitions. Now that's one of the performance improvement that you saw in the query. In case of I have the here, which is the case when I was doing the load session, when I was clicking a session, you saw that the results were not very different, because in that case also I was passing a single partition and the query was going to a single partition. In this case also the same thing will happen, but here the partition key will have the third field also. So when I use a hierarchical partition key, I have got an advantage of using either all 3 keys, which is the full path, or a partial path by just providing the first 2 levels. I could also say just I can also just have the first level and have a partition key with only 1 field. Of course, in that case, the query will be a little performance wise a little degraded, but not as degraded as this case, because in that case I'm passing as no partition key. So that's the logic of using a hierarchical partition key. Again, this is all good, and you can call it concepts, etc. But maybe let's taste the pudding. Let's try this in the real application and see how it performs. So to do that, I'm going to my application settings and I'm going to change this to the HPK collection that we just talked about, and then train the application. Okay, now we have the 100K collection, but hierarchical partition key running. And let's repeat the same steps and see what numbers we see. So step number 1, I'm going to click on a session and see what kind of numbers we see. Okay, we are seeing around 4.5 RUs, 60-second latency. Very good. This was very good numbers, but this was not a problem area earlier also. So we will move to the next step, which is to say, what do we see when we load the sessions again? So I click on refresh and let's see what happens. Okay, the RUs have come down. The latency also has come down. And finally, let's do the search and see whether it works.
This was the maximum issue that we
Yes.
originally saw.
Yeah, so the RU, if you remember, this had like around 900, if I remember correctly, in my last example, and this was around 3,500 or 5,000. So there is a huge dip in the RUs and latency. So I think my suggestion of using hierarchical partition key will hold true here, and it solves the problem. So this is a very simple but effective way of solving the problem. I would like to reiterate, your partition key can make or break your application. So select your partition key very, very carefully. So let's revisit the numbers once more so that we are clear on what we saw. We saw that after changing the hierarchy partition key, the query performance had improved. We saw drop in RU charges. When we looked at the list session, it called, we saw some big dip in latency as well as RU. And the search was a killer where we saw a huge dip in case of latency and RU.
This is great. This is great. Just in this context, maybe just also want to talk of pagination and how important is it before we conclude today?
Absolutely. Oh, absolutely. Maybe I can just walk you through that also. So pagination is, this is not something that the customer reported, but maybe I can demo that also. So, okay. So in pagination, what we are basically saying is, when we were analyzing this customer's workload, we saw that there was some chat sessions which were very, long, which means they had 1,500 messages, large number of messages. And the design was to load all the messages together. So which I thought was not great, and it was taking a lot of RUs. So maybe let me do is let me first show you how it would be, the experience would be if pagination is not there. So in this case, right now, pagination is on. When we turn it off, let me search for that long chat. Okay, and now we have this large chat which has got a large number of messages. Let me try loading that and see what kind of numbers we see. So something that was taking around 4 RUs normally now is taking 32 RUs, and again it's taking higher number of time to load. Now, if I were to repeat the same exercise once again, but with pagination, let's see what happens.
Here we are doing the same search, loading up a really large document.
Yeah. So we have found the same large chat session here. And again, I'm going to now load this, but this time it is going to be run with pagination on. So we are expecting the RUs to be less. Oh yeah, as soon as you saw that RUs were around 10, 12 RUs and the latency has come down. So, and now if there are older messages, I can keep getting them in steps. So here, an example where I could break a large request into smaller requests. I saw that the latency reduced. I also saw that total RUs that it consumed was less. So it's a good design to, whenever you are pulling a large amount of data, or if possible, do it in pages so that you can reduce your RU load as well as improve your latency.
Thank you, Sandeep. So I think we will stop today's session, the first part. Key takeaways, gotchas on this part. Whenever we see degradation in performance or issues on performance, definitely we need to look at partitioning. We need to look at our query metrics and stats and try better optimization such as pagination and things like that. In our part 2, the next video session, we will be looking at another optimization best practice, things around, hey, what happens if your application crashes? For example, when you go from prototype to production and your volume increases, suddenly the app crashes instead of scaling up. What can we do about that? With that teaser, I'll let you go on this session. Thank you very much.
Thank you.